Hi, my name is Michael Fairby, and I work in Dr. Oshie Sinyal's Molecular Transport and Separations Lab at WVU. Our group is part of the Department of Chemical and Biomedical Engineering in the Statler College. Currently, our projects focus on forward osmosis membrane development for unconventional applications, in this case, produced water treatment. Produced water is wastewater that is left over from oil and gas extraction. This type of water tends to have salinity levels over 75,000 milligrams per liter. This creates an excessive osmotic pressure. Reverse osmosis membranes and nanofiltration are unable to treat the water due to excessive pressure. Although these membranes aren't chosen for produced water treatment, these conventional techniques account for over 65% of the seawater desalination market. Overall, membranes are preferred for wastewater treatment because they are cost-effective and scalable. Lastly, they are low energy processes when compared to other separation techniques like distillation. The traditional reverse osmosis membranes work by overcoming the pressure gradient formed by the membrane by adding hydraulic pressure to the system to facilitate the separation. This is commonly used in the food industry and wastewater treatment, where the salinity is less than 75,000 milligrams per liter. Forward osmosis membranes facilitate diffusion using the pressure gradient without added hydraulic pressure. This process is found in nature with plant roots and cells and is used in different industries with water treatment over 75,000 milligrams per liter. On the opposite side of the feed solution is a draw solution, which is used to make the pressure gradient. This solution should be inexpensive and low fouling. When developing our membrane for forward osmosis, we focused on the support layer, which contained a lot of the interconnectivity. The support layer was manipulated based on thickness, polyelectrolytes, and post-treatment. Our membrane development incorporated the layer-by-layer process using two oppositely charged polyelectrolytes, PAH at pH 8.5 and PAA at 3.5. with washing steps of deionized water at pH 3.5 and 8.5. The post-treatment consisted of submerging the membrane in deionized water at pH 2 for 5 minutes, then air drying it. Finally, it was heated to 180 degrees Celsius for 2 hours. The membranes were fabricated using a custom 3D printer designed for low viscosity inks in Dr. Costa Sierro's lab. The two polyelectrolytes were used as inks and were applied using single-layer meandering film technique. An initial pressure of around 7 kilopascals was needed to start printing a layer. The rest was printed using capillary action. Each of the layers was distributed by the surface tension. After the print of the positively charged PAH, a washing step of water with pH 8.5 was done. Then the membrane was dried with an air hose. Similarly, a layer of negatively charged PAA was printed, then washed in pH 3.5 and air dried with a hose. This circuit was performed multiple times till a membrane of 11.5 bilayers and 20.5 bilayers were produced. The membranes then underwent post-treatment to ensure porosity and stability. SEM images, like Figure 1, of the top and cross sections of membranes were found. The pores present in image C are formed by rejected water by the membrane. The interconnectivity is seen in the cross-sectional images, both A and B. It is formed by positive charge of the amine group by acid treatment, then the charge repulsion in the polymers. The structure is then stabilized after the heating step of the post-treatment. Polymers, deposition time, and acid treatment, pH, all affect the support layer interconnectivity. In terms of this experiment, the deposition time was consistent at around 3 minutes, which was the printing time. We are currently working on testing the molecular weight cutoff to describe the pore size distribution and membrane retention. This is achieved by testing the rejection of a polysaccharide at different molecular weights. The aim is to have about 90% rejection, and that will provide a great general porosity of the membrane. Both continuous and batch processes are being used to test the membrane molecular weight cutoff. This undergraduate research was funded by the National Science Foundation EPSCoR project, improving water management, treatment, and recovery in oil and gas production.